The Elastic Compute Cloud, as I mentioned, is the ability to launch a machine image, either one that we've created, one that the community has published. For example, there's scientific Linux machine images that are out there that you can launch and then extend and then turn into your own derivative machine images. But a wide array of Linux operating systems, many Windows versions. And then you specify when you're launching 1 or 1,000 instances, running an instance is a running virtual machine based on that machine image. You specify where you want to launch it. You specify the instance type or the size of the virtual machine, selecting from a various arrays of compute, memory, storage characteristics, and also in the case of HPC, networking infrastructure they might want to use. And then we launch those, and within a few minutes, they're available and ready for you to run. If you're running our high-performance computing instances, you also have the option of creating a placement group, which would allow all instances within that placement group to have 10 gigabit full bisection non-blocking bandwidth. So what that means is that if you have a latency sensitive application, an MPI cluster, for example, you could define a virtual network topology within the cloud that would allow that application to run quite well. If you're running something like a embarrassingly parallel workload, on the other hand, you could use a placement group if you like. Probably won't take advantage of that if it's really embarrassingly parallel. In that case, you might even provision any number of instances across multiple availability zones or even across multiple regions. So I'll provide a couple of examples of that. Over time, of course, we continue to explore new hardware technologies. For example, when the Sandy Bridge processors came out, we launched those a few months before they were publicly released. Customers could access those servers in our cloud. Recently added SSD-based instances. So if you need 125,000 IOPS from a single virtual machine, we can deliver that capability now. And as new processors come out, we'll make those available within our fleet and let you consume those on an hourly basis. In terms of pricing models, at a high level, I wanted to mention this, not because this is a sales pitch, but more because I think there's some very interesting capabilities that we offer. So the default model of using AWS is on demand. And what that means is that you pay by the hour for any hour that you're running your server. When you turn it off, we stop charging you for it. And so if you have a workload that is embarrassingly parallel or even fairly parallelizable, what that means is that you can run 100 servers for 1 hour at the same cost as running one server for 100 hours. So at no additional cost, you're getting 99 hours of competitive advantage if you're in the commercial sector, or 99 hours earlier, you're going to get your result sets back. And so it's a nice model to have. On-demand is the most expensive way to run instances in the cloud. And so we also offer something called reserved instances. And reserved instances allow you to specify upfront. You pay a small fee, and then in exchange for paying that fee, we'll do two things. One, we'll reserve some capacity for you, so you always have access to the size of virtual machine that you wanted in a specific data center or availability zone. And then any hour that you're running that machine, we'll charge you less per hour than we would if you were running that just on the on-demand, the walking up to us and saying, hey, I need a bunch of instances, can I launch those? So by giving us some visibility into your capacity needs, you can save money and also get a guarantee that capacity will be available. And that's reserved instances are very appropriate for predictable workloads, things like database servers, or if you have a cluster that's always going to look the same for at least a year period or even for some number of months. It's a good way to save money and ensure availability of that capacity whenever you need it. Spot model is one that's very, very interesting for scientific customers. So the spot market, we have a pool of capacity that we keep on hand in order to ensure that we can always give on-demand customers access to the infrastructure that they need. And so we've got this pool of capacity that we monetize by setting it at a variable price. So whatever the market price is what we would charge you for it. If you want to launch a server that's normally $2.40 an hour, on the spot market, typically that's going to be maybe 50 cents an hour. And so you would place a bid that says, I'm willing to pay up to 75 cents an hour for the server. And then maybe that first hour or the first 8 hours, it would only be 50 cents an hour. If other people come along and want that instance type in that availability zone, the price would start to go up a little bit. We would only charge you each hour based on whatever the market price is. If, however, somebody comes along, they're working on a paper for Supercompute, or they've got a large genomics workload that they need to process in a hurry, and they need just a ton of capacity, they might actually bid above the on-demand price. And as a result, we're going to turn off your instance and give it to that person and charge them more per hour than you were willing to pay by the hour. And then when they finish up their workload, you would have the choice. You could either resume that work or launch the instance again at that lower price, or you could say, oh, I don't really need it now. If you needed to get your work done in a hurry, you could also go back and either increase your bid, or you could launch under the on-demand or reserved instance model. It's only under the spot model that we will actually turn off your instance and give it to somebody else. If you launch under on-demand or reserved, you have your servers until you turn them off. And under reserved instance, you always have the ability to launch your servers whenever you want. This eye chart, I won't go into it in detail, but it just talks a bit about the different families of servers that we have, ranging from the micro, the T1 micro that allows you to have burst capacity CPU. It's the only instance type that gives you that kind of variable CPU performance. All the others have a fixed amount of CPU. All of our instance types have a fixed amount of memory, so we're not going to over-provision memory, and you might start to see things swapping behind the scenes. You'll have exactly the amount of memory that you're expecting. But if you're running something like a database server, you might use the high memory instance types. If you're using an embarrassingly parallel workload spread across thousands of nodes, maybe you'll use the standard instance types. If you have a CPU-intensive workload that doesn't require a lot of memory, we have an instance type that can optimize for that, all while keeping costs as low as possible. And then on the high-performance computing side, we actually have 4 types now, 2 of which are shown here. We have Nehalem-based systems, our CC1 Quad XL. We have the same configuration, but also with 2 NVIDIA Tesla Fermi GPUs. In addition to that, we recently launched the Sandy Bridge-based CC2 8XL instance, which gives you more than double the performance of the CC1s at less than half the cost. And if you're using something that's vector math intensive, the AVX extensions that come with the Sandy Bridge are going to be really, really useful for folks. And then very recently, we added SSD capabilities with our high I/O instance types that give you 2 1 terabyte SSD lines. In aggregate, you can get at least 125,000 IOPS out of the server. So it's very common for researchers to build, for example, a Gluster cluster on top of the HI1s, these high I/O instance types, and then supplement that, have compute actually running across a Sandy Bridge if it's an MPI type workload, or if you're using, if it's more of an embarrassingly parallel workload, maybe use one of the other instance types that, where you get lots of them at a very low cost. So what are people doing with this? Well, they're building some of the world's largest virtual supercomputers in the cloud. This is just a snapshot of the 42nd largest supercomputer in the world that was built on Amazon Web Services. We have a pharmaceutical customer that through one of our partners, Cycle Computing, built a 30,000 core cluster for $1,279 an hour. They recently built a 50,000 core cluster for a similar workload that was at the same price or just slightly more than that. Our prices have dropped, and they were able to actually build out even larger clusters. So it's not just about. I want to emphasize that it's not just about being able to build massive, tens of thousands of node clusters in the cloud. What's really far more important is the ability to have access to this programmable infrastructure. So today I'm actually sitting at NASA JPL. Lots of fun activities coming up for the Mars Science Laboratory landing on August 5th. Everybody should tune in, happening at 10:31 p.m. Pacific time. But at JPL, as you can imagine, and much like every other national laboratory, NASA facility, many research institutions, there are hundreds and thousands of researchers, all of whom could benefit from having access to maybe a 10 to 20 teraflop supercomputing cluster for kind of what if analysis, having a place to kind of test some ideas. And so JPL, anybody who wants to provision a cluster can do so literally with a click through one of their provisioning systems that calls Amazon Web Services behind the scenes. In 5 minutes, they have access to a cluster. There's not a lot of friction involved with actually spinning up a workload on that cluster. They can feel free to experiment at scale, not just running on one or two machines, but across a larger set of machines. And the cost is actually really low. And so what this means is that instead of having 100 researchers all trying to schedule time on a shared computing infrastructure, every one of them can have access to perhaps a smaller cluster of their own, still a very powerful cluster at a very low cost. And then as those large workloads come in, they can decide whether they want to run that at JPL supercomputing facilities, at NASA Ames, where there's a massive supercomputer, UT Austin, one of the other supercomputing facilities that we have in the country, or do they want to build that out on the AWS? And so this flexibility and the fact that a cluster can be defined and provisioned and available to actually do science in a few minutes means that researchers are now asking far more questions than they would have otherwise. And there's actually examples, well, I'll get to in a moment, of missions that actually wouldn't have been able to continue to operate but for access to this type of infrastructure.